Hey, this is Workbench for Workbench Quagmire. It is day 71 of our free code camp Python certification in 100-ish days. We're on a section about algorithms, and we're on our last theory section here. So let's get started with how do maps, hash maps, and sets work. In this lesson, we'll go over maps, hash maps, and sets. But before we do that, let's define abstract data types. An abstract data type, ADT, is a conceptual representation of a data type, including what operations can be performed on the data and the properties of that data. Abstract data types are like blueprints that describe what operations can be performed, not how they can be performed. They separate the interface from the actual implementation of the operations. A map is an ADT that manages collections of key value pairs and their operations in a very specific and efficient way. In a map, every value is associated with a specific key. One of the key characteristics of maps is that every key must be unique. This uniqueness allows for direct lookups, which makes the process of retrieving information much more efficient. Only keys must be unique. Values can be repeated. The map abstract data type also defines important operations such as inserting key value pairs, getting the values associated with a key, and updating the values associated with a key, removing a key value pair, and checking if a key exists in the map. It doesn't exactly specify how these operations should be performed, it is just lists them as a part of the available operations of the data type. A hash map, also known as a hash table, is a concrete implementation of the map abstract data type. Hash maps use a technique called hashing to perform common operations very efficiently. Hashing essentially works by generating a hash value for each element using a hash function. The hash value is generated based on the key of the key value pair and is used to calculate an index in an underlying array, the actual data structure where the key value pairs are stored. But you might be asking yourself, what happens if two keys result in the same index? Hash maps solve these collisions with clever strategies. One option is to use the chaining strategy, where each array index points to a linked list, another data structure where all the elements with the same index are stored. Another strategy is to use open addressing, which involves searching for the next available index in the array based on a predefined search technique. The average case time complexity of a hash map is constant time for inserting, retrieving, and deleting key value pairs. The worst case time complexity of these operations is linear time, O to the n. Each operation when there are many hash collisions, which occurs when there are many hash collisions, so the collision resolution strategy has to be applied multiple times. The space complexity of inserting into a hash map is a constant 1 on the average case and a constant amount of memory to store the new pair. However, the worst case, it can have a linear complexity due to the resizing operation of the underlying array. In general, removing an element has a constant space complexity of 1. This turns the hash table into something similar to a linear data structure where in elements have to be scanned to find the target key. However, this is relatively rare if the hash map is implemented properly. Python dictionaries are implemented as hash maps behind the scene. To create a Python dictionary, you just need to write the key value pairs within curly brackets and separate them with a comma. Each key should be separated from its corresponding value with a colon. So we're familiar with this here. In the code, A is the key and 1 is the value. Alternatively, you can use dict, as in my dictionary, dict, and then there's your keys are A, B, and C, and your values are 1, 2, 3. And you can get the value through its corresponding key, my dict A. You can also update the value through the associated key, my dict A equals 4, and you can remove the key value pair with the delete keyword, delete my dictionary A. You can also check if a key in the dictionary or not, using C in my dictionary. And you can call these methods to get the key, value, and items for the dictionary respectively. My dictionary keys, my dictionary values, and my dictionary items. This is all stuff we learned previously. Great, now that you know more about maps and hash maps, let's talk about sets. Sets are unordered collections of unique elements. We've talked about sets before too. Let's break this concept down into key components. Sets are unordered. The elements of a set are not stored in any specific order, so you cannot access them through indices. Sets only contain unique elements. If you try to add the same element twice, only one copy of the value is kept. They are analogous to sets in mathematics, and they implement the same set operations like intersection, union, and difference. One of the main advantages of sets is that they guarantee that the elements will be unique, no duplicates. This is why they are often used to remove duplicates from a list or other data structures. They are also dynamic. They can adjust to the number of elements that are currently stored. This makes them quite powerful. The average case time complexity of removing, getting the length of the set, and checking if an element is in the set is constant time, 1, which is very efficient. Since sets are implemented as hash tables, the worst case time complexity of adding, removing, and checking membership is linear time. This may occur when there are multiple hash collisions, transforming the hash table into something similar to a linear data structure, where n scans are required to find the key. In terms of space complexity, in the average case, inserting an element would have constant complexity, with a unique element requiring a constant amount of memory. However, in the worst case, there could be a resizing operation of the underlying array, which could take linear space complexity. In general, removing an element would take constant space complexity. Python has built-in set data structure that you can use to work with sets in your programs. Behind the scenes, Python sets are implemented using a hash table where only the keys are stored without any associated values. Sets can only store objects of immutable data types because their hash values always remain the same. In contrast, the hash values of mutable objects can change when they are mutated. That's why they cannot be part of sets. If the hash value of an object stored in the set changes, the program would not be able to find it anymore. To define a set in Python, you need to surround the elements with curly brackets and separate them with commas. So numbers equals a set 1, 2, 3. To create an empty set, you can call set. Note that if you use empty curly brackets, automatically create a Python dictionary, not a set. So you must call set function to create an empty set. You can add an element to the set with the add method. So number.add5. You can also remove elements from the set with remove method. So number remove 5. This will throw a key error if the element is not found, but if you don't want to throw an error in this case, you could use discard method instead. The pop method returns an arbitrary element from the set, while the clear method removes all the elements from the set. You can test if an element is in a set with the in operator, so 5 in numbers. Python also supports set operations, including unions, differences, symmetric difference, and intersection, which can be performed with these methods. So set A, set B, so 1, 2, 3, 4, and 2, 3, 4, 5, 6. Set A union set B, set A union set intersection set B, set A symmetric difference set B, and set A difference set B. Or with their equivalent operators, set A, and here's all the operators. The average case time complexity for adding, removing, and testing membership in is constant time. The worst case time complexity for these operations is linear time because of the hash map's worst case collision scenario. You can also check if a set is a subset or a superset of one another using the is subset or is superset. In general, you should use sets when you need to store a collection of unique items and frequently check for the presence of an item. Maps, hash maps, and sets are powerful data structures designed for efficient data organization and retrieval. Each one of them has its own unique characteristics and use cases. As a developer, you'll need to choose the best one for the project. So what is the fundamental difference in the type of data stored by a hash map or map compared to a set? Hash maps store ordered collections while sets are unordered. That's not true. Hash maps store unique key value pairs while sets store unique individual elements. That's true. Hash maps cannot store duplicate values while sets can. That's not true. Sets are used for numerical data while hash maps are used for textual data. So the best choice is 2. What is the main mechanism that allows hash maps and sets to achieve average case of 1 constant time performance for operations like insertion and lookup? They keep all elements sorted. That's not true. They store elements in linked lists, allowing quick traversal. That might be true. They use a hash function to compute a direct memory location for elements. I think that's our correct answer. They always store a very small number of elements. That's not true. In the context of the hash maps and sets, what is a hash collision? That's when an element is successfully found. Nope. It's when an element is inserted at the beginning. Nope. It's when a hash map runs out of memory and needs to resize. Nope. It's when two different keys or elements produce the same hash value. That's, I think, see how we did. We did. We are done with our working with common data structures theories lessons. And next time we will tackle this build a linked list workshop. So thanks for watching the video. Don't forget to comment, like, and subscribe, and I'll see you next time for our Build a Linked List workshop.